Hi. Kiki doesn't seem to have arrived yet, so perhaps I could fill in some time by showing you a trick I've been rehearsing. I usually save this trick for a time at the party when the drink supply is getting a little bit on the critical side. Here we go. I always say there's nothing like a nice glass of Beaujolais. And believe me, this is nothing like a nice glass of Beaujolais. Hello,
Hi.
Kiki.
What are you doing there?
I'm just pouring some wine. I made it myself. Would you like some?
I'd love some, yeah.
Ah, okay.
Hey.
Ah, well, there you go. Magic doesn't work for just anybody.
Just the sort of sneaky trick you'd expect from a chemist. Later on, I'll get Ian to show you how it's done, and you'll see it is just a trick, inspired not so much by divine providence as by an unbending law of nature, the equilibrium law. And that's where I come in. I shall try to develop this rather abstract idea by drawing on Ian's experimental observations, suggesting explanations, as well as making some predictions for him to try out. Now, we've decided to build our story around the properties and reactions of aqueous acids, like these: hydrochloric acid and acetic acid. The simple formula we've used for acetic acid reflects our belief that an acid is a substance that yields hydrogen ions in aqueous solution. In other words, we believe that both acids are dissociated into ions in aqueous solution, giving hydrogen ions and chloride ions, or hydrogen ions and acetate ions. But how do we know this is true? Is there any way of testing for the presence of hydrogen ions in a solution?
Well, yes, there is, on this apparatus called a pH meter. Now, don't worry about the concept of pH just now. It is described in the main text. Basically, it's just an alternative and sometimes more convenient way of expressing the hydrogen ion concentration. This electrode is sensitive to the hydrogen ion concentration in solution, and in the beaker I've got some 0.1 molar hydrochloric acid. I'll just note the reading of the hydrogen ion concentration from the scale. Well, I make that 10 to the minus 1, or 0.1 molar hydrogen ion concentration, and I'll just note that for future reference. Now, are we to expect the same behavior from all acids? What will happen, for example, if I replace this hydrochloric acid with some 0.1 molar acetic acid? Watch the needle as I add the acid. The concentration of hydrogen ions is now 10 to the minus 3 moles per litre. That's quite a difference. In other words, the number of hydrogen ions produced by the acetic acid is 1/100th that produced by the same concentration of hydrochloric acid.
So, both solutions do contain hydrogen ions, but there's quite a difference between them. The concentration of hydrogen ions is about 100 times less in this solution than in this one. In this case, we start off with 0.1 moles of hydrochloric acid, and we end up with the same amount of hydrogen ions. In other words, hydrochloric acid is fully dissociated in solution. It's a strong acid. By contrast, acetic acid is obviously not fully dissociated. It's a weak acid. And that's the crux of our story. When we dissolve acetic acid in water, an equilibrium is set up between undissociated acid on the one hand and dissociation products on the other. And what does that mean? Let's look at a mechanical analogy. I'm sure you'd agree that these scales are balanced. They're in equilibrium. But is chemical equilibrium like this? For instance, does the dissociation of acetic acid just stop so that we end up with a static situation of reactants balanced against products? No, it's not like this at all. Chemical equilibrium is dynamic. It's more like trying to walk up a downwards moving escalator. You keep moving, but you don't actually get anywhere. The trouble is that there's no really convincing experiment we can show you to get across this idea. So we've devised a little game. Okay, Ian, you've got the game set up.
Yes, I think I've got it sufficiently rigged to ensure a favourable result.
Okay, so we play it on this board. Notice there's a dividing line across the middle. So this is my territory, and that's Ian's. Now I start off with 20 red counters spread randomly on my side, together with one special counter, the attacker. Ian doesn't have any red counters, just the one yellow counter, the defender. Now for the rules. My attacker can move 2 squares, 1 or 2 squares, in any direction, like this, for example. When it hits a red counter, that's transferred to Ian's side. So from my point of view, the object of the game is to get as many counters as possible across onto Ian's side.
Now my aim is to resist Kiki's advances. I've also got to try and get the counters back to her side of the board. And to do this, my man can move 3 paces on either side.
Shall we have a game then?
Right.
Right. Let's speed up the action a bit and see if we can change things. I'd like you to keep a check on the numbers on Ian's side. Doesn't look as though we're getting anywhere anymore, does it? It's as though some sort of stalemate is building up.
The
here.
change is certainly slowing down anyway.
Yeah. Shall we go on a bit?
Oh yes, I think just to give you a chance.
Okay.
Actually, I think you should exceed defeat. It's remaining pretty constant.
Yeah, I think I'm going to give up.
Yeah, it's a bit of a bore. Let me make it easier for you. Let me just take all these counters away. How would that be?
Great. Okay. Now let's see you win.
Yeah,
It looks as though it's happened again, doesn't it?
Yeah.
It must be that somehow the rates of these things must be equalizing. It must
Yes.
be that the rate at which I'm getting them across to your side is getting to be equal to the rate that you're putting them across to my side, so that overall the numbers on each side don't change with time any longer.
That's true. Certainly the rates are the same now.
Why do you think that is? I guess it's because although my counter isn't as agile, I've generally got a higher concentration on this side.
Therefore a greater chance of meeting one of your counters.
That's right. Whereas you've got the more agile counter.
And therefore can return faster, having a lower concentration of counters on this side.
That's right. Well, pretty frustrating as a game because no one's ever going to win. And of course, we knew it would end like this. We set up the rules to create a situation that mirrors the dynamic equilibrium in a chemical system, like our acetic acid. So with this analogy, we'd have undissociated acid on this side and the dissociation products on Ian's side. At equilibrium, undissociated acid is dissociating and the dissociation products are recombining, but at the same rate, so that the relative proportions of the two different species don't change with time. Now you saw what happened in our game when we disturbed the equilibrium by removing all the counters from Ian's side. I was able to get rid of a few more of my counters, but eventually a new equilibrium was set up.
So what do you predict will happen if we throw in acetate ions to our chemical system? Well, sodium acetate is a good source of acetate ions. If I tip some out, we can see that it's a nice crystalline solid. It's readily soluble in water. And like all salts, is fully dissociated into ions in solution. Let's see what happens when we add this acetate to our acetic acid solution. I've marked the original concentration of our acetic acid on the pH meter, and we'll follow the reaction as I add the acetate. There's another dramatic decrease in the hydrogen ion concentration. In fact, it's decreased almost 100-fold.
So, we start with a solution containing molecules and ions in equilibrium. But when we add more acetate ions, the system is knocked out of equilibrium. But it rapidly compensates for this imbalance. Some of the added acetate ions react with hydrogen ions to form more undissociated acid until a new equilibrium is set up. In terms of this equation, what we've done is to shift the equilibrium over to the left. Alternatively, we could have shifted it in the other direction by removing either of these components from the solution. For example, it's easy enough to remove hydrogen ions by adding hydroxide ions, because they react together to form water. So, it looks as though chemical equilibrium really is a dynamic situation. Inside this peaceful-looking solution, there's actually a ferment of activity on the molecular level. Now let's see if we can use this idea to understand Ian's party trick. Well, the key to the mystery is an indicator called phenolphthalein. It's got a rather gruesome molecular formula, so we'll simplify things and write it like this. Again, it's only partly dissociated into ions in solution. This equilibrium is set up. Now, its use as an indicator depends on the difference in colour between the molecular form, which is colourless, and the ion, which is red. Now let's have another look at that trick.
Before we talk our way through this trick, it is important that you realise that phenolphthalein is particularly poisonous. And therefore, if you try this trick at home, it is important that you do not drink any of the liquids involved. Now back to the magic. I start off with a solution of distilled water, and I lace this with some phenolphthalein solution. The hydrogen ion concentration in this solution is sufficiently high that the molecular form of the indicator predominates. When I take this solution and pour it into my decanter, what my audience thinks is water is converted into wine. Now, can you see how this has been rigged?
Well, I can. He obviously had a drop of sodium hydroxide in that flask, enough to hook out hydrogen ions and shift the equilibrium over in favour of the red ionic form.
Hey, just whose trick is this anyway?
I was only trying to be helpful.
She's right, of course. Now, to complete the trick, I take some concentrated hydrochloric acid, and I use this to lace this glass. Now, this ensures that when I add the wine, the molecular form of the indicator will be regenerated, and apparently, water will be reformed.
Well, that's cleared up our little mystery. It all rests on manipulating this equilibrium. We can shift it backwards or forwards by adding or removing hydrogen ions. So far, so good. But we can go a stage further. All of our hints about equilibrium suggest that there should be some sort of relationship between the concentrations of the different components in an equilibrium mixture. There is. It's called the equilibrium constant. For our indicator, this particular ratio of concentrations, H plus times IN minus divided by HIN, must always have the same value at equilibrium. That's why it's called the equilibrium constant. Okay? Now, I can't prove to you that this is true, but Ian can show you how to find out whether it is.
Okay, now we're going to measure an equilibrium constant. But first of all, let me tell you a story. This fellow went into his doctor's and says, "Doctor, I'm not feeling too well. I think it's something I've been drinking." And the doctor said, "Well, what do you expect if you've been drinking meths? What you really want is a nice glass of whiskey." Well, we now realize that this isn't a magic trick. It's the same as the water into wine, except that I've replaced the phenolphthalein in this solution with another indicator, one which is yellow in acid and purple in base. But now watch what happens if I place this purple solution into this instrument. Just put it in, and away we go. It's good, isn't it? But here's the clever part. Now watch what happens when I put some of this yellow solution into the instrument. I'll just reset the table. And off we go. It's a clever instrument, isn't it? It can differentiate between the two colours. But not only that, it can measure the quantity of light absorbed as the absorbance at any wavelength that we choose. Now, the important point is that this absorbance is directly proportional to concentration. And so this instrument gives us a direct measure of the concentration of a species. And so absorption spectrometers such as this are very useful instruments. You're going to use one when you go to summer school. But why exactly is this solution purple? Let's look again at the spectrum of this solution. Most of the absorption occurs between 500 and 650 nanometers. Now the visible spectrum looks like this. Watch what happens when we absorb wavelengths between 500 and 650 nanometers. The greens, yellows, and oranges are removed from the spectrum, and the rest of the light, which is transmitted by the solution, contains the blues and reds, giving a purple solution. No wonder the instrument can differentiate colours. So how does the instrument work? Well, the light beam from the lamp in the spectrometer is split into two, and both beams pass into the sample compartment. One beam passes through the sample cell and is partially absorbed. The other beam is passed through a reference cell which contains the solvent only. The instrument then estimates the amount of light which is absorbed by comparison of the reduced intensity from the sample cell to that passed through the reference cell. Fine. But what are these solutions that I have picked? The indicator that I have chosen is bromophenol blue. We can manipulate this equilibrium by control of the hydrogen ion concentration. In a highly acid medium, the acidic yellow form will predominate. In alkaline conditions, the purple ionic form will predominate. But what's going to happen in an intermediate situation? At a hydrogen ion concentration between these two extremes, such as in this rather insipid-looking solution here. When both molecular forms are present, what do you predict will happen to the spectrum? Remember, the spectrum of the ionic form looks like this, and that of the acid form like this. In our intermediate case, the spectrum looks like this. Not surprisingly, there are two peaks, since both colored forms are present. Furthermore, because of the relationship between absorbance and concentration, I can calculate the concentrations of the two species at equilibrium. So believe it or not, we are now at a stage where we can calculate an equilibrium constant. The ratio of the concentrations of IN minus to HIN, as estimated from the spectrum, is 1.77. The hydrogen ion concentration, as calculated from the pH meter, is 5 times 10 to the minus 5 molar. And so the equilibrium constant, which is the product between these two, is equal to 8.85 times 10 to the minus 5. But is this value of K that we've measured truly a constant? We've repeated the experiment for solutions of two different acidities. The data are reproduced in your broadcast notes. I'd like you to calculate K from these and convince yourselves that with an experimental error, you truly obtain a constant value.
So our story comes full circle. We started off by concentrating on acids, especially weak acids like acetic acid and most indicators, which are only partly dissociated into ions. A dynamic equilibrium is set up, which is characterized by the equilibrium constant K. Now, it's through the size of this constant that the equilibrium law exerts its implacable control over a chemical reaction. Quite simply, the size of K determines how far the reaction can go, the proportion of our starting materials that we can hope to convert to product. But are we to be hidebound by one particular value of K for a given reaction? Is there nothing we can do to change the value? I want you to think about these questions while you watch Ian's final experiment.
I've got an equilibrium mixture in this bulb, consisting of two gases, N2O4 and its dissociation product, NO2. The brown colour of the mixture is due to the NO2. Now I'm going to raise the temperature of this system and leave you to interpret the result. Now let's compare this with the cold gaseous mixture. So what has happened to our chemical equilibrium?